Welcome to our webinar today about teaching design of experiments. I have some opening remarks. The objective of this webinar is not teaching you about DOE. There are other excellent resources for this, as we will see later. Today, I'm going to show examples, best practices, and free resources supporting you teaching DOE using JMP. Being an engineer myself, I'm excited about what we have to offer, about the impact for students, the engineers and scientists of tomorrow, and for industry, which is desperate for these problem-solving skills, including our customers. You will see a broad range of tools and resources to choose from. And if you just pick a few, I'm sure you will boost your teaching activities. For example, let's look at this result based on this design data table. So JMP told us, using this table, how to control the reaction to collect only 13 measurements of yield by controlling these factors. Let's look at the result from this experiment. The summary of the analysis shows clearly which factors are significant, explaining yield. So time is the most significant one, then temperature and modifier, all with their low and high values. And there are also one two-factor interaction and one quadratic term for time. We also see that the two factors, agitation and pressure, are not in the game anymore. So they are not significant at all. The profiler down here shows the response curves in each dimension, modifier, temperature, and time, or for each factor. And the profiler visually confirms two linear and one nonlinear relationship for time. We can slide through every dimension by changing one input at a time to see the effect on the output, which is yield. We can even see the interaction between modifier and temperature. So that's this significant interaction here, which can be visualized using the profiler. Looking for the best settings, giving the highest yield, of course, JMP helps again. We learn that we should go with high modifier, high temperature, and a higher value of time, but not the maximum. Let me just tidy up a bit and go on. So today I will skip the general introduction to JMP. If you are totally new to JMP, you can get a 30 days trial version of JMP at jmp.com/trial to open this journal file and to explore the links and all the further information yourself. The next topics will be, after a short motivation, that we will look at the role of the software, the tools, which can really change how you teach DOE. Other topics are then about resources, both in class and online resources. And before we wrap up, I will present a brand new offering, our package for doctoral training in sciences and engineering, which core component is also a 2-day DOE course. Stay tuned. So, why is design of experiments a game changer for so many users? We have many excellent resources explaining why to design experiments. One of them is the blog series of my colleague Phil Kay. This is a 7-part series giving you 7 good reasons why to design experiments. Here are my top 3 arguments. First, design experiments are in 99% of all problems more efficient and more effective than trial and error or one factor at a time experiments. This means better results with less effort. More real-world systems have interactions going on, or most real-world systems have interactions, in which cases you may find the best solution only by using DOE. And second, experiments collect new data following a statistically designed test plan. The plan tells you how to control the factors simultaneously and keeping everything else fixed. And this is the only approach which can tell which factor changes are causing an effect you see on your response. So this cannot be replaced by mining any observed data, no matter how big your data are. And third, innovation requires to study something new, which was never observed before. So you have to test these new ideas in a lab environment anyway. And again, the best approach driving innovation is a designed experiment. And why teaching DOE? If any approach proved to be successful in many ways, so then the practitioners should use them, right? So 2 years ago, also Imperial College London asked the chemical industry in the UK about the most relevant skills to solve their problems. And no surprise, the winner was DOE. And this outcome, and also listening to our customers worldwide, shows that DOE is relevant for many students. But looking at the engineering curriculum, you see that in statistics courses, they typically end at simple linear regression, and DOE is a multivariate problem. Also, data science courses, we see more and more, and also machine learning courses, they focus on prediction rather than understanding a system or a process. So DOE courses can really provide an opportunity to teach more students problem-solving skills and statistical thinking. And many companies have to train their employees on the job. They complain about a huge gap between skills they need and methods taught at universities today. Let us close this gap by more teaching DOE. The JMP academic program offers academic licenses, and academic resources. Let us look at the software first. I want to demonstrate that JMP has unique benefits also in teaching. The JMP capabilities for DOE can also be checked out on the JMP starter window. So here I just choose DOE, and we get a nice overview about all the platforms which support designing experiments, from optimal design, the custom design platform, and augment design, modern ways to design experiments, including definitive screening designs, classical traditional textbook designs, diagnostics, and even several special purpose designs. Looking at these capabilities, we can say that JMP tools are the most comprehensive tool set on the market. They are also the most advanced tools. So we gave a joint presentation at one of our recent Discovery Summit conferences together with KU Leuven, and the researcher from the Department of Biosystems shared a case study, and he said, for this problem where we were seeing a highly complex setting that might involve batch-to-batch variation in addition to mixture variables and process variables, and also observable but uncontrollable factors. So with all that complexity, they said JMP was the only DOE tool we could use to solve a problem of this complexity. And third, JMP is also a very, very relevant tool set. It has the typical workflow, a typical way of thinking, which is also used in industry. And if you want to see examples how industry solve their problems using JMP DOE, please check out the customer stories. You can just click on that link and then read customer stories on your own. So are these tools also easy to use, really following an intuitive workflow, and are they engaging students? I would like to come back for my live demo. I would like to come back to my teaser example, this reaction experiment, where we saw the modeled relationship in the JMP profiler before. So here on the data table, we see this is a JMP design table, and the design is a definitive screening design in this case. The nice thing in JMP is that all the phases are integrated. So this is really in the middle of the whole study. So the experiment was already done. So we see the measurements are already in our response measurements. So now we are ready for the analysis. But you also get stored scripts on the design table to go back and to look at the design phase again, and that's what I want to show you. First, I just click this script, which is created by JMP, to go back at any time. And here we see how this design was created. So we see the response was specified, and an interesting point here is that JMP typically asks the user, what is your goal? What do you want at the end? At the end of this experiment and the analysis, what do you want to see? And we want to see the maximum yield and understand how to get this. So the goal is to maximize, and we also have a lower limit set for yield. So yield should be above 75%. We also have in this case 5 continuous factors like pressure, modifier, and so on. They are all continuous with their low and high values. So these are the ranges. And then this is a typical definitive screening design. So JMP uses the low and high values for each factor, but also adds a pair with center points for each factor, like this one and this one and this one. And then finally a global center point. That's the last row, number 17. And for the data table, we did not select to get 4 extra runs. So I will show you that in a second. But I also wanted to show you why the definitive screening design is so efficient. Here you see that there's no aliasing, no correlation between main effects and 2-factor interactions. Another benefit is that for this type of problems, a definitive screening design does the screening plus the optimization in a single, or from the data of a single experiment. Now I can even go back further. That's the very first step using the definitive screening design tool. You specify the response and factors, click continue, and this is the option where you could just add 4 extra runs as suggested by JMP, because this gives you a significant win on power for estimating the model effects. So for this table, this was set to 0, then make design, and then another click make table. And we got this table with an empty yield column, but then the measurements are done. And now we are ready to analyze the experimental data. And for that, you get stored scripts, analysis scripts as well. So there's a screening, a model, fit definitive screening script added to the design table. As soon as you have your response or responses measured, you click on the green triangle and you get a first fit definitive screening result. I don't want to go into the details here, but from here I want to make a model, and this is the model launch window using the fit model platform in JMP. And you see that we have the response set here, the yield, and then the model effects we want to analyze, we want to estimate are our 3 main effects. And then in this case we have 1 interaction and 2 quadratic terms, 1 for modifier and 1 for time. So we want to see screening results first. That's the emphasis set here, and use multiple regression standard least squares to fit the data. So clicking run gets us to this result here. So this is one of the diagnostic outputs. We see the actual versus the predicted yield, and this looks quite reasonable. So also the R square is very high, so almost 100%, so that's almost perfect, and the whole model is significant. So this is definitely much better than just guessing the mean. Now we see the summary again. The summary is interactive, so if you think, let's simplify our model because this bottom effect here, modifier times modifier, is not significant on the edge, but it's not significant, so I can select it and remove it from our model, and now it's gone, and we are left with these higher significant effects. I also close some other diagnostic information which is shown by default, and we get back to this profiler again. So let me also tidy up a bit. So just to get some more space, because I want to add something else to the profiler in a second. So if you trust the model, and we saw that there are many diagnostics you can explore. If we then think this is a useful model, let's use it. So you maybe want to explore the hyperdimensional space, which is also defined by a model equation, an expression, this one here. But you typically don't want to read this, because this does not really help to see what's going on. So what else? There are also some other visual options as profilers. So you could also look at the contours and then changing yield, and I could also change the grid a bit. So you could look at a contour profiler for 2 dimensions, and that's the point. This is temperature by modifier, and we see the yield contours. We could also look at time by modifier, and here you see the quadratic nature of this surface. So this is basically limited to 2 dimensions. And most problems have more dimensions than 2. Also, the surface profiler can help with some visualizations, but again, this is limited. We have 2 dimensions, 2 factors set at the base here, but the 3rd dimension is yield. So again, we can pick 2 dimensions to see the surface, the response surface for yield for these 2 dimensions, but that's it. So the prediction profiler shows us factor by factor. So this is not limited by the number of factors you have in one graph. So that's a very nice thing about the profiler. So this is about real-world problems, right? So this is the theory so far, that we think, okay, this is the model, and then let me just remove the desirability functions, because we know what we want. We want high yield. And I also switch to the best settings again. So now we see the best settings. And then you get a message from the process or system engineer telling you, hey, this is wishful thinking, that I can fix the temperature to 420 all the time. So that's not what we can expect. But what can we expect? And this can be added to the optimal settings by using the simulator. So what we expect is maybe some jitter here on our measurement system for yield. So for yield, I can add certain kind of noise to have some jitter there. We also may have and expect some random variation of temperature. You can specify the shape of the distribution, can be also uniform or other distribution, and the spread and the mean. So maybe this is what we expect, where the temperature will be. So the same for modifier and time. And now clicking simulate, we are simulating 5,000 values of yield at the optimal settings, but with the random variation of our 3 factors and some added noise for yield. And with this variation, so looking at a more real world setup, we see this is our lower limit, and this tail of the histogram of this distribution, the yield distribution, these are the defects which are below 75%. And we can expect around 1% of defects if this is our setup. And so the profiler can also combine multiple responses or also the same response from different models. So looking at this example here, so this is about tire production, car tires, and in this example we build a model or even some models for different responses. So we are interested in abrasion, but we are also measuring modulus and elongation and hardness. So we have 4 responses in this example. And these are the 4 responses we have here. And we can build the tires using 3 components of material. So we can use silica, silane, and sulfur at different amounts. And then the question is, how do we get the best tires? What is best? So the top 2, the higher the better. We want to maximize again. But elongation and hardness, we want to match a target. So these 2. So the desirability function tells us we want to be there. We want to match this exact value. Can we get there? Doing this manually is a bit tricky. Also because of the interactions and so on. So again, JMP helps us maximize the desirability, and that's an overall optimization now. So these are the amounts, how to set our 3 components to get the best tires. So these 2 targets are met, and the other 2 are as high as possible. Let me close this one and the data set as well, and this one here. So many courses introduce some basic concepts using a classical textbook design. And they can be found on the JMP DOE menu, and then look at the classical submenu, and I will show you a screening design. Maybe 80-90% of all the experiments in industry are screening designs. If you choose a classical screening design, you get to this platform, another simpler dialog, because you have less flexibility here. And let me specify this response. We keep this. So we want to maximize a single response called Y. Of course, you can double click and edit the name, but I don't want to lose time with editing right now. For the factors, I choose to add 3 continuous factors. So they get just dummy names here, and a low and a high value, which can be also set to other values, of course. I will again keep the default here. And I also add two level categorical factors. So here we see that we have 3 continuous and 2 categorical. And then I click continue and choose from a list. And now I get a list of screening designs, different screening designs with and without blocking. So we don't have blocking in like day by day variation or batch by batch variation. We don't have this in our experiment here. So I just take a design without blocking. Maybe let's start with 12 runs and a Plackett-Berman design. Let's see what we get here. So before we create the design table, we can look at the diagnostics, and we see that the power, the probability to detect an active effect is quite high. So we probably won't miss anything. But if we look at the correlation and the aliasing, so we see that we even have a correlation between the main effects and the two-factor interactions. That's this block here. So there's correlation everywhere, also for the block, so between interactions with other interactions, two factors. It's symmetric, so we just need to consider this half here. So there's aliasing everywhere. So if we want to be more sure on our results, let's go back and choose another one. So if I take maybe the next one, 16 run fractional factorial design, and now you can see very nicely the differences and what you win. So on this fractional factorial design, if we look at the correlations now, oh, this is much cleaner, much better. So this looks good. But if we look at the power, oh, it's just 25% power or likelihood to detect an effect which is really active. So we get a 75% chance to miss an active effect. That's not what we want, maybe. So I try a third one, and then we say, okay, in this, let's go and spend 32 runs. And you can also compare a full factorial design, and looking at the diagnostics now, we see, oh, the power is perfect, so we will detect everything. We won't miss any active effect. That's nice. There's no aliasing, so no uncertainty on the results, what is causing a response change. So this looks really perfect. If you want to use this, you just make the table and you get the table. In this case, you see the response is empty, the response column. And now it's time to measure the responses run by run. And we have 32 measurements to take. By the way, this is a full factorial design. And if we look at the distributions here, we see the low and high values, or the levels 1 or 2 for our 2-level categorical factors. And if I choose maybe the high level for x3, we see that all the other factors are balanced. The other factor settings. So this is a nice property you would like to see, and you can confirm this easily visually using the distribution platform. We close this one and this classical screening design, because for a fully tailored design, the custom designer asks about all requirements step by step and creates a new custom design which is optimal, called an optimal design, according to a certain criterion. So let me show you the workflow here as well. So this works like a wizard. So choose custom design, which is actually the first platform on the DOE menu. I take the same setup, so one response, and then I add 3 continuous factors. And here you see that we can have many other factor types, including covariates. So these are factors you can measure but not control. Mixture effects, blocking. So there's really a huge flexibility factor types you can mix. So I choose 3 continuous ones and the same procedure, 2 categorical 2-level ones. Yeah, so now we see continuous categorical. We also see easy to change. Yeah, so that's another flexibility in the custom designer. So if maybe x3 would be temperature, somebody could say, oh, it's really, really hard to change the temperature from low to high or vice versa. So this needs days or weeks. Yeah, so in this case, you could say, okay, let's specify this factor as hard to change, and then you get a split plot experiment. Yeah, so just another option you get on the custom design. Yeah, I click continue. Yeah, we can set constraints, also nice. Then you can spend the tests in the space which is more interesting. Yeah. The model is the model we want to estimate. So this is what we want to learn about. Yeah, and if I choose response surface model, adding interactions and quadratic terms, so we got a warning, no quadratic terms for categorical effects. Okay, that's okay, we know that. But now we have more effects, more parameters we want to estimate, and that of course needs more runs, higher budget. Yeah, we could say, we can even spend more the better, or we can only spend 24 runs or reduce the number of runs. We need 19 because we have this number, probably 19 parameters we have to estimate. So that's really the minimum. Yeah, I go with the default here. I make the design. And now JMP creates a custom design for us. Brand new and optimal for our problem. Yeah, so this is the design plan. So the settings we have to set. Again, we can look at the diagnostics. And I would like to show you another option here, simulate responses, because this is very nice for teaching. So now I make the table again. So that's this table here. And in addition, I get this control window where I can set the model parameters. So we typically don't know. We typically want to estimate by this experiment. Here I say there's nothing going on. So like this, 0. So there's nothing going on. Everything is 0. And then I apply this. And this Y simulated has a formula. So this looks up what I configured on the control window and simulates a response. And there's nothing happening. Everything is 0. Yeah, but if I say, okay, I know that x1 has a coefficient of 1. Yeah, so now I can apply this, and now you see that this changed. Yeah, so you can see that we get a simulated response here. Also say that x2 is maybe -2. Yeah, and x4, the first level, is also 1. And temperature, the quadratic term, is also active. Yeah, and now I click apply. We get a more complex response structure. And now I also add an error. And now you can show what you would get from your experiment, assuming that these are the true parameter, the true coefficients, and that we have an error of this size. And it's quite nice to look at this graphically. And here I can add the simulated Y, and I can also add the x1. And if I now apply, you see how the output changes. I could also look at x2, and we see this even steeper. We could look at temperature, where we have a quadratic effect going on. You can see always with an error. Yeah, so this would be maybe misleading, but there's always a chance to be wrong. And by clicking apply, you get a random error. So you can really see what an experiment would give you and what the uncertainty would be. So this is really nice for teaching. I could also add the categorical factor here, and then we also see that the level 1 of x4 is typically higher above level 2, and that's because we have this coefficient going on here. It's a bit cheating because you typically don't know this, but just to play with your design table, simulating a response is a really nice feature. And as a final example, I would like to show you something more advanced. So what if the response is not just a target value, but a target function we want to see as output? So this is also a sample data set, and here we have several batches we measured over time, and this is a milling process. So we really want to get this response, this size down. These are particles, and we are milling them to reduce them in size, in nanometers. And how to do this? These are the 4 factors. And we want to know how can we do this in the best way. So we can look at all our batches, and we see at different factor settings how the size gets down over time. And we see this one down here, the green one, the target. This is really how we want it to be. We want to go down very fast and then stay stable in the green zone around the target. That's what we want to be. And how to solve such problems, this is the Functional Data Explorer in JMP. And this can help you with this one, with this type of problems. So here we see all our batch data, and all the batches are already modeled using B-splines in JMP. And on the data processing step, we already set this target function as our target. So that's the golden curve we want to see, the ideal outcome. Our target. So we modeled all the batches. So the red curves are the models here. And what we get are then components. So we have this mean component. So that's a base shape. And then we have an additional shape component, which is this one, just one in this case. And these are 2 components, and this is like principal component analysis, and these are actually functional principal components. And you can see them in the profiler here. And so this one would be at a weight for the component 1 of minus 83. I could also enter down here minus 83. And then we get a function like this, and you see this. If we remove, or if we move up on the first component, we are changing our function like this, and that's more in this corner in our space. But we don't want to understand how this reacts on a principal component. We want to understand how this changes based on our process settings. And this is the function now. And again, maximizing the desirability does an optimization here. And this tells us high percentage of beats and strengths, and a low flow and a high temperature give us the closest output closest to our golden curve or target function. So this is functional data analysis. The platform is called Functional Data Explorer, and that's a quite new platform in JMP Pro. Summing up, what makes JMP unique for teaching DOE? So JMP DOE, especially the custom designer, have an unbeaten flexibility, but the tools are still very easy to use. So no programming needed, just point and click. Context menus, the red triangles, offer always tests and options, which make sense in a certain analysis context. So that's really data-driven and intuitive. Interactive visualizations, especially the dynamic linking of selected data, and supports EDA, exploratory data analysis. So maybe you don't need to build a model. You can just click and see what's going on and at least get some first ideas. And the profiler is the #1 tool in JMP to communicate what you learned from an experiment and to discuss the action to take next. I would like to spend a few minutes also pointing you to academic resources. So if you consider to using JMP in your DOE course, there's no greenfield. Yeah, you should also check out our resources available, especially for teaching DOE, of course. And a good starting point is our course material library. And that's this page here. So you can click on this link if you download the journal, which will be posted in a few days. Download the journal. If you don't have JMP, get the trial version of JMP, and you can also click the links. You can try everything yourself. And this is the page I'm talking about, a collection of resources, a variety of different resources, including the one-page guides, which are helpful for DOE. So these are single pages, how to set up a screening experiment, how to evaluate and compare designs. Some other videos and resources, you are pointed to some useful webinars and also textbooks. I also have a few textbooks I would like to recommend on my journal. So there's this quite famous textbook by Peter Goose and Bradley Jones. And this is a book based on case studies. Yeah, so it's really, really entertaining to read, and you learn a lot. You get a lot of best practices, real world problems. Every case study is different, has different types of additional problems to solve, and you see how to do this with the help of JMP. This is a brand new book, also from Brad Jones, but with Doug Montgomery. And you can also get the slides and the data sets from an instructor page and use it in your course. This is a supplement for the most famous book so far on design of experiments. That's the one by Doug Montgomery, which is used by the majority of DOE courses, at least in the UK. And I also want to suggest this book here. So this is about understanding variability and designing experiments. And this is really, really a good book about statistical thinking and what engineers should be aware of. This book here also comes for free, by the way, Jumpstart Statistics, with a chapter on DOE. If you register for STIPS, our online course, I will mention in a minute as well. Yeah, so this here, I would like to mention, these are the course materials, so-called teaching kits. They are from SAS Education. So they are typically used by SAS trainers for corporate training courses. For academic use, you get them for free, and you can use all the slides, all the data sets, the exercises, the quizzes. You get a full set of instructor notes you can use for your courses as well. These are the courses which are available for teaching DOE. So you see that there are different types of DOE courses: classic design, custom design, screening designs, mixture designs. And I would like to show you the quality of the instructor notes. So here we look at the custom design course, chapter 2.2. So this is introducing testing with a continuous factor, just one continuous factor. And you see there are slides with additional comments, just very few formulas, a lot of hands-on demos and exercises which are all explained step by step. You see the outputs, everything is discussed. There are also many simulators which simulate, for instance, the impact of selecting the range of a factor. So here you get a testing at a very small range, and then you make the range broader and bigger, and then you get a much better picture. This is all interactive and simulated by using the course content. There are also online resources which can be used. And I would like to start again with the e-learning courses from SAS Education again. And here we have two of them. So these are full courses. So the SAS e-learning courses, they take up to 16 hours, and they are included for free in all academic site licenses of JMP. So unlimited use, all students can take a course, maybe before your course or after your course. So you can combine them in any way, or just set them to certain parts of a course if you like. The next one, the second recommendation for online resource, is our Statistical Thinking online course. And this is also quite new, just a few years old, but very, very famous and used so widely, because this course teaches in 7 modules all the relevant skills which are required to solve real-world problems. And for DOE, I suggest to look at the modules Statistical Thinking and Problem Solving, but of course also look at the DOE module. So all these modules, the whole course is for free. It's online. You get access to JMP Pro in the cloud. You get also a digital badge you can share on social media. And for blended learning, we are also happy to share course content, including the PowerPoint slides, data sets, and technical summaries for use in your classes. That's the online course Statistical Thinking for Industrial Problem Solving. Just Google JMP Statistical Thinking and you will get to this page. And finally, the last idea here is developed by our colleague and also delivered quite recently by Phil Kay. So this was targeting at chemistry. It was a workshop called Smarter Experimentation for Chemists, 5 modules each. And you get also the link here. And the workshop is still online. And it has 5 sessions. So an introduction, and then factorial experiments, then screening designs, response surface designs, optimization, and tips and tricks and best practices. There's also hands-on you can do using the Jump trial version, and there's also a certificate you can request. And last but not least, I would like to mention our new offering for doctoral training. And this is called Jump Academic Suite, which is our academic license for doctoral training in sciences and engineering. And this package, this offering, was designed for centers for doctoral training, master programs, and similar programs in the areas of chemistry, biotech, pharma, science, and engineering. And this is the page where you can get more information. The core component here, as you see here, the core component is really a 2-day DOE course. And we deliver this course. We also provide some train the trainer to make you independent, also teaching the same course. You get everything you need from us. And let me show you the journals. So this is the course journal you get with all the data sets, all the slides, all information. Introduction starts also with a helicopter experiment just to set the stage and some other discussions. Then we introduce experiments with one categorical factor to introduce ANOVA. We also introduce experiments with one continuous factor to recap regression. And then we look into definitive screening designs, so screening, optimization, and simulation. And then on the second day, we use the custom designer and augment design, the standard workflow, the most flexible one. There are several advanced topics and a more freestyle project for additional hands-on for the students. And we are closing with some tips and tricks and best practices and discussions as always. So if you're interested to learn more about this offering, go to jump.com/doctoral training, and there you see what's included. You can also watch a webinar, because this was developed together with Imperial College in London, and you can see a joint webinar with Ben Deadman from Imperial in chemistry, and watch the webinar. And if you're interested to deploy this training program also at your university, just click this button and we get back to you, and we will discuss your needs and maybe schedule the implementation of this new program. So wrapping up, there are always more links to explore, but that's for you. So just get the journal, as I mentioned, some more interesting links, I think, which could not be shown because of time restrictions. Where should you start? This is my top 5. Don't miss these types of resources. Check them out. They can really be a great kick-off for developing your DOE courses. And of course, stay in touch. So there's the Jump community where you can discuss best practices or anything with thousands of other Jump users worldwide. If you want to keep to stay in the loop and get updates in the future, also opt in, jump.com/opt-in, so to receive Jump news and important updates. And that's what I wanted to mention. I'm sorry that we are at the end of the hour, but I'm available also for questions if there are any.